3 coronal mass ejections, 3 direct hits, 1 interstellar visitor, and somehow, impossibly, it didn't even flinch. What you're about to hear defies everything we thought we knew about how matter behaves in space. This isn't speculation. This isn't science fiction. This is happening right now, caught on instruments we've trusted for decades, and nobody, not NASA, not ESA, not a single astrophysicist willing to go on record can explain what they're seeing. Stay with me until the end, because what happened after that third strike changes everything we thought was possible in our solar system. In March 2025, the Sun is in one of its active phases, which means it's throwing tantrums across the inner solar system. Solar flares, magnetic storms, and coronal mass ejections, those billion-ton clouds of superheated plasma that move at speeds up to 3 million kilometers per hour. These aren't gentle cosmic breezes. When a CME hits Earth, it can knock out power grids, fry satellites, and paint auroras across skies that haven't seen them in generations. They're weapons of pure stellar fury, and we've watched them obliterate comets, strip atmospheres from smaller bodies, and fundamentally alter the trajectories of anything unlucky enough to be in their path. Now imagine that force, that incomprehensible violence aimed not once, not twice, but 3 times at a single target. A visitor from beyond our solar system, travelling through the inner regions where the Sun's influence is absolute. This object, catalogued as 3I Atlas, came from somewhere in the constellation Perseus. It's been moving through our neighbourhood for months now. Silent, predictable, following the mathematical certainty of gravitational physics, until March 17th. The first coronal mass ejection erupted from an active region near the Sun's equator at 0342 UTC. Solar observatories caught it immediately, a massive plasma cloud expanding outward, like a fist opening in slow motion. By the time analysts ran the trajectory calculations, they knew. This CME was on a collision course with 3I Atlas. Impact was predicted within 18 hours. The object was roughly 400 million kilometers from the Sun at that point, well within the zone where CMEs maintain their coherence and destructive potential. Scientists around the world prepared their instruments. This was going to be spectacular. A direct hit on an interstellar object, something we'd never witnessed before. The data alone would be invaluable. 18 hours and 12 minutes later, the plasma wave struck. Coronagraph footage from SOHO and STE-REO satellites captured the moment. You could see the expanding cloud engulf the region where 3I Atlas should have been. The brightness, the electromagnetic chaos, the sheer scale of the impact, it was everything the models predicted. And then came the second CME, less than 6 hours after the first. This one originated from a different active region, almost as if the Sun had coordinated a follow-up strike. The odds of 2 independent CMEs targeting the same moving object within hours of each other are astronomical. Not impossible, but vanishingly rare. Yet there it was, another billion-ton hammer falling toward the same cosmic nail. The third CME launched 43 hours after the first. By this point, the scientific community was no longer treating this as coincidence. Something was happening that fell outside normal solar behavior. 3 eruptions, 3 trajectories, all converging on the same interstellar visitor. The plasma impacts overlapped, creating a sustained bombardment that should have been catastrophic for any known object. Think about what happens when a comet gets hit by even a glancing CME blow. The coma flares, the tail distorts. The nucleus can fragment entirely if the impact is strong enough. We've seen it happen, we have the data, we know what to expect. But 3I Atlas didn't do any of that. When the first impact cleared and observatories reacquired their lock on the object, it was still there. Same trajectory, same velocity. No visible distortion, no outgassing, no fragmentation debris. It was as if nothing had happened. Scientists double-checked their calculations. Maybe the CME had been weaker than estimated. Number. The plasma density readings were solid. Maybe 3I Atlas had somehow moved out of the impact zone at the last moment. Number. Positional tracking confirmed direct hits. Maybe the instruments had malfunctioned. Number. Multiple independent observatories across 3 continents captured the same impossible result. The second hit produced the same outcome. Nothing. And the third, still nothing. By March 21st, the data was undeniable and utterly inexplicable. An object roughly half a kilometre across had absorbed 3 direct coronal mass ejections without measurable consequence. No deflection, no structural damage, no reaction whatsoever. It simply continued on its path, as if the sun had thrown cotton balls instead of apocalyptic plasma storms. Now, here's where it gets truly strange. While 3I Atlas remained unchanged, the sun didn't. Within hours of the third CME impact, solar activity in the region surrounding the object's trajectory began to spike. New active regions appeared. Magnetic field lines reorganized in patterns that didn't match standard solar weather models. It was subtle at first, the kind of thing you'd miss if you weren't specifically looking for it. But by March 24th, the sun's behavior had shifted enough that space weather forecasters were noting anomalies in their reports. The star that had just thrown 3 punches seemed to be reacting to something. Not cooling down, not calming, reacting. Ask yourself this question, and really sit with it for a moment. What kind of object survives 3 billion-ton plasma impacts without flinching? What kind of physics allows something to remain completely unaffected by forces that reshape planets? And most unsettling of all, what does it mean when the sun, our massive fusion reactor that's been burning for 4.5 billion years, appears to change its behavior in response to something that just shrugged off its most violent outbursts? I'm asking you to comment below right now. Tell me where you're watching this from. Tell me if you've heard about this anywhere else. Because what I'm about to show you in the next few minutes isn't just about one weird space rock. It's about what happens when the impossible shows up in our cosmic backyard and forces us to question everything we thought was certain. Hit that like button if you're ready to go deeper, because we're about to examine the recovery data that's making veteran astronomers lose sleep. The story doesn't end with those 3 strikes. It begins there. And what emerged in the days that followed the readings, the anomalies, the patterns that shouldn't exist, that's where this investigation truly ignites. You need to understand something fundamental before we continue. Space is not empty. Space is not forgiving. And when something moves through it as if the rules don't apply, we're no longer talking about astronomy. We're talking about something else entirely. When the plasma cleared and the sun's fury subsided, scientists expected to see damage. They expected debris trails, compositional changes, trajectory deviations, all the telltale signatures of an object that had just endured cosmic violence. What they got instead was perfection. And in science, perfection isn't reassuring. It's terrifying. Because perfect outcomes don't exist in nature. Nature is messy, chaotic, governed by probability and statistical variation. When something emerges from catastrophe completely unchanged, it means either your instruments are lying, or your understanding of physics is incomplete. Neither option brings comfort. The recovery observations began within hours of the third CME dissipating. Observatories worldwide reoriented their instruments toward 3I Atlas, hungry for post-impact data. The James Webb Space Telescope allocated emergency observation time. Ground-based infrared arrays in Chile and Hawaii extended their monitoring windows. Even amateur astronomers with serious equipment joined the coordination effort, creating a distributed observation network spanning 5 continents. Everyone wanted the same thing to understand what they'd just witnessed. The data started flowing back immediately, and with each new dataset the confusion deepened. First came the trajectory analysis. When massive plasma clouds impact an object in space, momentum transfer is unavoidable. It's basic Newtonian physics. The CME carries kinetic energy and mass. When it collides with a target, that energy has to go somewhere. Even if the object is incredibly dense or has unusual structural properties, you'll see some deflection, some velocity change, however minute. The calculations are straightforward. Given the estimated mass of 3I Atlas and the measured characteristics of the 3 CMEs, the expected trajectory deviation should have been somewhere between 2 and 7 arcseconds over a 48-hour period. That's tiny, but it's measurable with modern instruments. It's detectable. It should have been there. It wasn't. Positional measurements taken before the first CME and after the third showed identical orbital parameters within instrumental error margins. The object hadn't moved. Not by 2 arcseconds, not by 1, not by any amount that multiple independent observation systems could detect. Trajectory specialists ran the calculations again, adjusting for measurement uncertainties, accounting for gravitational perturbations from Jupiter and Saturn, factoring in solar radiation pressure. Nothing changed the conclusion. 3I Atlas had maintained perfect orbital stability through events that should have pushed it, however slightly off course. Then came the spectroscopic data, and this is where things shifted from puzzling to genuinely unnerving. When plasma impacts an object, especially plasma as energized as CME material, you get electromagnetic interactions. The surface heats up. Molecules get excited. If there's any volatile material, ice, frozen gases, organic compounds, it sublimates, creating a temporary atmosphere that spectroscopes can analyze. We've seen this happen with every comet ever struck by solar wind or CME events. It's reliable, it's predictable, it's how we learned what comets are made of in the first place. 3. iAtlas showed none of this. Spectroscopic observations captured during and immediately after each CME impact revealed no changes in the object's emission or absorption spectra. No temperature spikes, no outgassing signatures, no ionization features that would indicate surface material reacting to the plasma bath. The object's spectral fingerprint remained as flat and featureless after the bombardment as it had been before. It was as if the trillion-degree plasma had simply flowed around it without touching, without transferring heat, without interacting at all. Some researchers initially suggested that perhaps 3 iAtlas was composed of extremely refractory material substances, with incredibly high melting points that could withstand brief plasma exposure without reacting. Tungsten, graphite, certain ceramics can handle extreme temperatures. But here's the problem with that explanation. The CMEs didn't just deliver heat. They delivered magnetic fields, charged particles, and electromagnetic radiation across the entire spectrum from radio waves to X-rays. Even the most thermally resistant natural materials respond to that kind of comprehensive energetic assault. Magnetic fields induce currents in conductive materials. Charged particles penetrate surfaces and cause secondary radiation. Something should have changed. Some signature should have appeared. Yet the coronagraph footage, those extended camera exposures that captured the CME impacts in progress, showed something that still doesn't make sense to observers who've studied the recordings frame by frame. During the height of each impact, when the plasma density around 3 iAtlas should have been at maximum, there were moments where the object appeared not surrounded by the CME but separated from it, like a stone in a stream creating a calm pocket of water immediately downstream. The plasma seemed to part around the object, flowing past it rather than through it, creating a void region that persisted for minutes at a time. This is not how plasma behaves in space. Plasma follows magnetic field lines. It fills available space. It doesn't spontaneously create exclusion zones around solid objects, unless those objects are generating their own magnetic fields strong enough to deflect the incoming flow. And that's the hypothesis that started circulating in the academic community by late March, that 3 iAtlas must possess an intrinsic magnetic field, something powerful enough to shield itself from CME bombardment. But the numbers required for that kind of deflection are staggering. We're talking about field strengths comparable to what you'd find around magnetars, those exotic neutron stars with magnetic fields so intense they warp the quantum vacuum. How does a half-kilometre rock generate magnetar-level fields? It doesn't. Not through any natural process we understand. The infrared observations added another layer of mystery. When objects in space are hit by high-energy events, they heat up. That heat then radiates away as infrared light over hours or days, creating a characteristic cooling curve that tells you about the object's thermal properties, how well it absorbs heat, how efficiently it radiates, what its internal structure might be like. Infrared telescopes watching 3 iAtlas captured this exact data set, and what they found was a cooling curve that made no physical sense. The object radiated heat at a rate suggesting it had an internal structure more efficient at thermal distribution than any known natural material. Heat that should have concentrated at the impact-facing surface seemed to distribute almost instantaneously throughout the object's entire volume, then radiate away with unusual uniformity. One planetary scientist I spoke with, someone who spent 3 decades studying asteroid thermal properties, described it this way. He said, imagine heating one end of a metal rod with a blowtorch. Normally, the heat conducts along the rod at a measurable rate depending on the metal's thermal conductivity. With 3 iAtlas, it was as if the entire rod reached the same temperature the instant the torch touched one end. Instantaneous thermal equilibrium across the whole structure. That doesn't happen with rock, it doesn't happen with ice, it doesn't even happen with the most thermally conductive metals we can manufacture. Yet the infrared data kept showing exactly that pattern across all 3 CME events. By early April, 2 weeks after the triple strike, the astronomical community had generated more questions than answers. The object's behaviour violated no absolute physical laws. Nothing it did was strictly impossible, but the combination of anomalies painted a picture that didn't fit any natural explanation. perfect trajectory, maintenance, zero spectroscopic changes, apparent plasma deflection, anomalous thermal behavior. Each piece individually might be explainable through some exotic but natural process. All of them together? That's when you start hearing phrases like unprecedented and requiring new theoretical frameworks in the academic papers that were already being drafted. But there was something else emerging from the data. Something that took longer to notice because it wasn't about 3i Atlas itself. It was about what happened around the object in the hours and days following the strikes. The solar wind in that region of space began showing structural variations that correlated with the object's position. Small-scale magnetic anomalies, plasma density fluctuations, particles that seemed to be following trajectories slightly bent around the location where 3i Atlas had been, even after it had moved on. It was subtle, easily dismissed as measurement noise or natural solar wind turbulence, but it was there, logged in multiple datasets, persistent across observation sessions. The space around where those three impacts occurred had changed, and the sun, that massive ball of plasma that had thrown those three punches, was about to show us that it had noticed something we were only beginning to comprehend. The sun doesn't have consciousness. It doesn't think, doesn't plan, doesn't respond with intention. It's a sphere of hydrogen undergoing continuous fusion, governed entirely by the physics of plasma, pressure, and magnetic fields. This is what every astrophysicist will tell you, and they're right. The sun is a machine, an elegant, powerful, incomprehensibly vast machine, but a machine nonetheless. So when I tell you the sun reacted to what happened with 3i Atlas, I'm not suggesting the star developed awareness. I'm telling you that its behavior changed in ways that correlate so precisely with those three CME impacts that calling it coincidence strains credibility to the breaking point. The first indicators appeared on March 22nd, barely 36 hours after the final CME struck. Solar observatories monitoring the sun's activity noticed something peculiar about active region AR3952, the region that had spawned the third coronal mass ejection. Instead of decaying and dispersing energy as active regions typically do after major eruptions, AR3952 intensified. Its magnetic field strength increased by 12% over a 6-hour period. New sunspots emerged within the region's boundaries. The X-ray flux emanating from the area jumped to levels associated with pre-flare buildups, yet no flare materialized. The region was energizing without releasing that energy, like a coiled spring being wound tighter and tighter. Then came the magnetic field reconfigurations. The sun's magnetic field is constantly shifting, this is normal. Field lines emerge from the interior, arc through the corona, reconnect, and sink back down in an endless dance of electromagnetic chaos. But the patterns that began forming in late March were anything but normal. Multiple active regions across the sun's visible hemisphere started developing magnetic configurations that mirrored each other. Bipolar structures aligned in parallel. Field lines connecting distant regions in ways that don't typically occur. By March 26th, solar physicists were documenting something they'd seen only a handful of times in decades of observation, a large-scale magnetic coherence spanning almost 40% of the sun's visible surface. What does that mean in practical terms? Imagine you're looking at the ocean during a storm. Waves are crashing in every direction, chaotic and independent. Now imagine suddenly half those waves start moving in synchronized patterns, as if responding to a single orchestral conductor. The individual waves are still following the physics of water and wind, but the overall pattern has shifted from chaos to coordination. That's what was happening with the sun's magnetic field. Individual active regions were still behaving according to plasma physics, but the large-scale organization had changed in a way that suggested something was influencing the system as a whole. Space weather forecasters noticed it first in the practical effects. Solar wind measurements at Earth, which take about 2 to 3 days to reach us from the sun, began showing unusual structure starting March 24th. The wind's velocity was normal, its composition unremarkable, but its magnetic field orientation was rotating with a periodicity that didn't match the sun's rotation rate. It was as if the solar wind was carrying information about magnetic structures that were evolving faster than they should be. Satellite operators dealing with space weather hazards rely on predictive models built from decades of solar observation. Those models started producing anomalous outputs. Predictions diverged from observations. Forecasts that should have been accurate within 10% were missing by 30 or more. Here's what made this particularly unnerving for the people watching it unfold. The center of all this enhanced activity, the gravitational point around which these magnetic reconfigurations seemed to be organizing, corresponded to the solar longitude where those three CMES had originated. Not the longitude where they impacted 3I Atlas that was millions of kilometers away by this point, but where they came from. The Sun's surface regions that had generated the plasma bombardment were now behaving as if they'd received feedback, as if the successful delivery of those three massive punches had triggered some kind of response protocol. I need to be clear about something. There is no scientific model that predicts this kind of cause and effect relationship between CME impacts on distant objects and subsequent solar activity changes. The energy scales don't work. A CME carries maybe 10 to the 32nd ergs of energy. The Sun's total energy output per second is 10 to the 33rd ergs. The idea that an impact event 400 million kilometers away could somehow influence solar behavior is like suggesting that clapping your hands in New York City causes a thunderstorm in Tokyo. The signal-to-noise ratio is infinitesimal. The physical mechanisms don't exist. Yet the temporal correlation between the 3I Atlas impacts and the solar activity changes was precise to within hours. By early April, 3 separate solar physics teams had published preliminary reports in the Astronomer's Telegram, a rapid response platform for astronomical discoveries requiring immediate community awareness. All 3 reports documented the same thing. Unexplained enhancement of solar activity correlated with the CME events targeting 3I Atlas, increased magnetic complexity, anomalous active region evolution, solar wind structure variations. The reports were careful, hedged with appropriate scientific caution, but the message was clear. Something unusual was happening, and it appeared connected to those 3 strikes. Then, on April 7th, something happened that erased any remaining possibility of dismissing this as statistical noise. A new coronal mass ejection erupted from AR 3952, that same active region that had been energizing for 2 weeks. This CME was different from the previous 3. It was faster, more tightly focused, and its trajectory wasn't random. Preliminary calculations showed it was aimed along the same spatial corridor where 3I Atlas was traveling. Not at the object's current position by now, 3I Atlas had moved substantially but along its projected path, as if whatever force was organizing these eruptions wasn't just reacting to where the object had been, but predicting where it was going. The 4th CME never reached its target. 3I Atlas's trajectory curved slightly due to Jupiter's gravitational influence, taking it just outside the plasma cloud's impact zone. But the intent, if we can even use that word, seemed clear. The Sun had launched another strike, and this one appeared targeted not by chance, but by extrapolation. Solar physicists had no framework for this. The Sun doesn't aim. It doesn't predict. It erupts, according to local magnetic instabilities and pressure buildups. The fact that this 4th CME launched along a trajectory that would have intersected 3I Atlas's path if not for a gravitational perturbation meant one of 2 things. Either this was a coincidence of such profound improbability that we should start questioning statistics itself, or something about the Sun's magnetic structure had become responsive to this object's presence in ways we don't understand. I want you to think about what this implies for a moment. Set aside all the standard explanations about statistical clustering and selective attention. Just look at the sequence of events as if you're seeing it for the first time. An interstellar object enters the inner solar system. The Sun hits it with 3 CMEs in rapid succession. The object doesn't react. The Sun's magnetic field then reorganizes itself over a 2-week period, culminating in a 4th CME launched along the object's trajectory. This reads like a description of 2 entities engaged in an interaction, a probe and a response, an action and a reaction, testing and being tested. If that description makes you uncomfortable, good. It should, because we're approaching territory where the data is starting to tell a story that our theoretical frameworks weren't built to accommodate. The Sun reacted, not in the sense of conscious decision-making, but in the sense of system-level behavioral change correlated with specific external events. And if the Sun reacted to 3I Atlas, then the natural question, the question that's keeping a small community of researchers awake at night is this. What exactly was the Sun reacting to? What property of that object, what characteristic, what signal triggered a stellar-scale response? And most importantly, was the response defensive, investigative, or something else entirely? Those questions lead us directly into the hypothesis that nobody wanted to say out loud until the data made silence impossible. Let me take you through a thought experiment, and I want you to follow this carefully because it's going to challenge some fundamental assumptions you have about how celestial mechanics work. Imagine you're an autonomous probe sent from another star system to study this region of the galaxy. You don't have orders. You don't have a mission control monitoring your every move. You were launched millennia ago with one directive: explore, analyze, survive. You've crossed the interstellar void using minimal energy, following gravitational contours, adjusting your trajectory only when absolutely necessary to avoid collision or gather data from proximity flybys. Now you're approaching a new star system, one with unusual characteristics, a yellow dwarf with a complex planetary arrangement and an exceptionally active stellar magnetic environment. What would you do? If you were designed with any level of sophistication, you wouldn't just fly through passively collecting telescope data. You'd want to know how this star behaves under stress, how its magnetic field responds to perturbations, whether its coronal ejections follow predictable patterns or show adaptive characteristics. You'd want to probe the system's fundamental physics to determine if it poses a threat to your survival or offers opportunities for energy harvesting, data collection, gravitational assist, or whatever your mission parameters prioritized. And critically, you'd want to do this without obviously revealing your artificial nature to any potentially observing intelligence native to the system. So here's what you might do. As you pass through the inner system, you position yourself in regions where the star's activity is high. You present a specific electromagnetic signature, something that might naturally trigger the star's instability thresholds. You become a target, but a carefully controlled one. When the star responds, and a star this active will respond, you measure everything. The plasma density, velocity, magnetic field strength, particle composition, electromagnetic spectrum, everything your instruments can capture. You take 3 strikes because one data point isn't enough. 3 gives you trend analysis. 3 reveals patterns. 3 lets you build a comprehensive model of this star's threat potential. And most importantly, you do all this while maintaining perfect trajectory stability, so that any observers studying you see only an inert object, a dumb rock following ballistic physics. You hide your intelligence behind the mask of passivity. This is the testing hypothesis, and before you dismiss it as wild speculation, understand that it emerged from trying to explain a very specific problem. Why would an object maintain such perfect stability through events that should have caused at least minute perturbations? The most straightforward explanation is active compensation, thrust vectoring, magnetic field generation, real-time trajectory corrections executed with enough precision that the adjustments fall below instrumental detection thresholds. We're talking about corrections measured in microns per second of velocity change. Tiny adjustments, but sustained and calculated, perfectly countering the momentum transfer from 3 separate plasma impacts. The physics of this aren't impossible. They're just implausible for any natural object, but they're entirely consistent with what you'd expect from an artificial probe equipped with ion drives or field generators capable of producing small corrective forces. The energy requirements aren't prohibitive. A sufficiently advanced propulsion system operating at minimal output could generate the necessary counterthrust without producing exhaust plumes visible to our instruments, especially if the system was designed for stealth, for operating in environments where being detected would compromise the mission. Now layer on the spectroscopic silence. No outgassing. No thermal signatures beyond what minimal heating any object would show. This suggests either an exotic natural composition or an artificial shielding system. Magnetic deflection of incoming plasma. Ablative surface materials engineered to absorb energy without vaporizing. Active cooling systems distributing heat throughout the structure, faster than passive conduction could manage. Again, each of these individually might be explainable through natural processes, but the combination reads like an engineering solution to a specific problem: how to survive close stellar passes while gathering maximum data without revealing your nature. Here's where it gets genuinely fascinating from an engineering perspective. If 3i Atlas is conducting a systematic stellar analysis, those 3 CME impacts weren't accidents or bad luck. They were orchestrated. Not by the sun is still just following its physics, but by positioning choices the object made. Think about the orbital elements. 3. Atlas approached the inner solar system at an angle and velocity that brought it through regions of maximum solar activity during a period when CME frequency was elevated. Coincidence? Possibly, but the trajectory also ensured multiple opportunities for close encounters with plasma events, while maintaining sufficient distance to avoid truly catastrophic scenarios like direct solar immersion. It threaded a needle, finding the sweet spot between data collection and self-preservation. And then there's the timing. The object arrived at perihelion, its closest approach to the Sun, during solar cycle 25's active phase. Solar cycles last about 11 years. They're predictable if you're observing from within the system, but how would an object launched from interstellar space thousands of years ago time its arrival to coincide with peak solar activity? Either remarkable luck, or the object made trajectory adjustments during its approach to hit this specific window. Small velocity changes executed over years or decades of travel could absolutely accomplish this, without being detectable from Earth until the final approach phase when we first spotted the object. Some researchers have explored whether the magnetic field hypothesis could explain all this without invoking artificiality. What if 3I Atlas is a fragment of a neutron star, something with an intrinsic magnetic field strong enough to deflect CMEs? The problem is mass. Neutron star material has densities around 10 to the 14th grams per cubic centimetre. A half-kilometre chunk would have mass comparable to a small moon, and would gravitationally perturb every inner planet as it passed through. Orbital mechanics tracking shows no such perturbations. The object's gravitational influence is consistent with normal density rock, ice, maybe some metal content, nothing exotic. So the magnetic deflection hypothesis, if true, requires an explanation beyond dense remnant star material. There's another angle worth considering, one that involves electromagnetic interaction rather than magnetic shielding. What if 3I Atlas isn't deflecting the plasma but short-circuiting it? Plasma conducts electricity. If the object carried a significant charge or could generate potential differences across its surface, it might create conditions where incoming plasma dissipates its energy through electrical discharge rather than mechanical impact. This would look like deflection, but would operate through different physics. The challenge with this model is sustaining the necessary charge separation in the conductive environment of space. Natural objects don't maintain large-scale electrical potentials for long, but a powered system with active charge management could theoretically do this, especially if it was harvesting energy from the incoming plasma itself to fuel the deflection mechanism. A self-powering shield, elegant in its efficiency. Let's address the elephant in the room. Is there any direct evidence that 3I Atlas is artificial? The honest answer is no. Everything I've described so far falls into the category of anomalous natural behaviour that raises questions but doesn't prove artificiality. We haven't detected radio transmissions. We haven't seen optical signals. There are no obvious surface structures visible in telescope images beyond what you'd expect from an irregularly shaped rocky body. The object could still be entirely natural, perhaps a type of asteroid or cometary nucleus, with properties we haven't encountered before. The universe is vast and old. Exotic natural formations are not only possible but statistically likely when you're sampling from billions of years of cosmic evolution. But here's what keeps the testing hypothesis alive in academic discussions: the Sun's reaction. If 3I Atlas is just a rock, even an unusual one, the subsequent solar behaviour makes no sense. Active regions don't energize in response to distant CME impacts unless there's a mechanism for feedback. But if the object was broadcasting some kind of electromagnetic signature during or after the impact, something brief, something we might not have been looking for because we weren't expecting it, that could constitute a signal back to the star. Not a message necessarily, but a physical response, reflected particles, induced magnetic oscillations, something that propagated back through the solar wind and interacted with the Sun's magnetic structure in a way that natural objects can't. This is where we transition from hypothesis to something more speculative but mathematically tractable. Several researchers have explored whether electromagnetic waves generated at the impact sites could travel back through the solar wind and affect active regions on the Sun. The answer is yes, under specific conditions involving plasma wave resonance and magnetic field line connectivity. If 3I Atlas generated such waves intentionally, or as a byproduct of its shielding systems, and if those waves coupled efficiently with the background solar wind plasma, they could carry information and energy back to their point of origin. The Sun wouldn't be reacting in a conscious sense. It would be responding to physical perturbations in its magnetic environment, perturbations caused by something that happened 400 million kilometers away, but transmitted through the solar wind as electromagnetic signals. This mechanism is testable. If correct, there should be detectable plasma wave signatures in the solar wind data from late March and early April. Waves with characteristics indicating generation at the 3I Atlas, impact sites and propagation back toward the Sun. Multiple teams are currently combing through archived solar wind measurements, looking for exactly these signatures. If found, it doesn't prove artificiality, but it establishes a physical mechanism for the Sun's behavioral changes and shifts the entire discussion into new territory. Territory where we have to seriously consider that this object, whether natural or artificial, possesses properties that allow it to interact with stars in ways we didn't know were possible. And if it was testing the Sun, gathering data through orchestrated plasma strikes, then the natural follow-up question becomes chillingly obvious. What did it learn? And what is it going to do with that information? Zero deflection. That's the number that refuses to go away. In all the noise, all the speculation, all the competing hypotheses about what 3I Atlas might be, there's one piece of data that stands like a wall every explanation must climb over. 3 coronal mass ejections struck this object, delivering combined momentum equivalent to detonating several million tons of TNT, and it didn't move. Not within instrumental error, not within the limits of measurement uncertainty. It held position as if the universe's most fundamental laws, Newton's laws of motion, had temporarily suspended their operations for this one special case. And that's the problem. Those laws don't suspend, they're not optional. So if 3I Atlas didn't deflect, something countered the momentum transfer with such precision that external observations couldn't distinguish it from a completely inert object. Something shielded it. Let's work through the mathematics of what that shield would need to accomplish, because understanding the engineering requirements helps clarify just how extraordinary this situation really is. A coronal mass ejection travelling at, say, 1,000 kilometers per second with a plasma density of 10 to the minus 15 grams per cubic meter centimeter, impacting a half-kilometer spherical object, presents a cross-sectional area of roughly 200,000 square meters. The momentum transfer over the duration of the impact lets estimate 6 hours of sustained plasma flow is calculable. You integrate the plasma density times velocity times area times time, and you get a momentum change that should alter the object's velocity by approximately half a meter per second. That's tiny. That's almost nothing in cosmic terms, but it's measurable, it's detectable, and it should have been there. To counter that momentum transfer, you need an equal and opposite force sustained over the same 6-hour period. For a magnetically based shield, that means generating a magnetic field strong enough to deflect incoming charged particles before they impact the physical surface. The field strength required depends on the particle's energy and the distance at which you want deflection to begin. If you want to create a standoff distance of several kilometers a bubble, within which plasma cannot penetrate, you need fields measured in tens of thousands of Tesla. For comparison, Earth's magnetic field is about 50 microtesla. MRI machines operate at 1 to 3 Tesla. The strongest continuous magnetic field ever generated in a laboratory is around 45 Tesla. We're talking about fields hundreds to thousands of times stronger than the most powerful magnets human technology has produced. Sustained for hours, powered by mechanisms that don't produce detectable energy signatures. That's the first problem. Power source. Magnetic fields of this magnitude require either enormous currents or exotic materials, with magnetic properties far beyond anything found in nature. Superconductors can carry large currents without resistance, but they require extreme cooling, and maintaining superconductivity in an object being bathed in million-degree plasma is, let's say, non-trivial. The alternative is using permanent magnetic materials, but even the strongest natural magnetic minerals, magnetite, for instance, can't produce fields anywhere near what's required. You'd need something that doesn't exist in our materials database. Something engineered, perhaps using principles of magnetic confinement that we've theorized but never implemented at this scale. But let's say you solve the power and materials problems. Let's say you have a magnetic shield generator buried inside this half-kilometer object, something using compact fusion or antimatter or whatever exotic energy source you can imagine. You still face the momentum problem from a different angle. The plasma might not impact the surface directly, but it's still transferring momentum to the magnetic field. The field is generated by the object, so ultimately the object still has to absorb that momentum. It's like catching a baseball with a glove versus your bare hand. The glove distributes the impact and protects your skin, but your hand still moves backward. The magnetic shield can protect the surface from thermal and electromagnetic damage, but it can't eliminate the momentum transfer, unless, and this is where we enter truly speculative physics, unless the field configuration is dynamic enough to redirect the plasma's trajectory in such a way that the net momentum transfer cancels out. An active deflection system that constantly adjusts its field geometry to guide plasma around the object in symmetric patterns, ensuring equal and opposite forces that sum to zero net effect. This is theoretically possible. It's called momentum vectoring, and we use primitive versions of it in ion propulsion systems for satellites. But doing it on the scale required to handle CME plasma flows while making it look natural, while leaving no detectable signatures of the active control systems, that requires a level of engineering precision that makes our most advanced spacecraft look like stone hammers. And yet, that's what the data seems to demand. An active, powered, continuously adjusting shield that maintained perfect momentum cancellation through 3 separate bombardment events spanning more than 40 hours. Now let's talk about the thermal problem, because this is equally vexing. The plasma from a CME isn't just moving particles, it's extraordinarily hot measured in millions of degrees. Even if you deflect 99% of it magnetically, that remaining 1% is still delivering enormous thermal energy. The infrared observations of 3I Atlas showed temperature elevations consistent with some heating, but nowhere near what you'd expect from even partial plasma contact. The cooling curves suggested the object was managing thermal load with impossible efficiency. Heat was appearing and disappearing faster than conduction and radiation could possibly account for. One explanation involves ablative shielding a sacrificial outer layer that vaporizes, carrying heat away from the main structure. Spacecraft re-entering Earth's atmosphere use this principle. But ablation produces gas, and that gas should be detectable spectroscopically. We should see emission lines from vaporized material, composition signatures telling us what the object is made of. We saw nothing, so if ablation was happening, either it was at such low levels that our instruments couldn't detect it possible, but unlikely given the energies involved, or the ablated material wasn't behaving like any substance we know. Perhaps it was ionizing instantly, and being swept away by the magnetic shield before it could form a detectable cloud. Perhaps the shielding was so effective that thermal loading was genuinely minimal, leaving nothing to ablate. There's another thermal management hypothesis that sounds like science fiction, but is actually grounded in legitimate physics: active heat pumping. If the object contained a distributed network of thermal management systems, think of them like advanced heat pipes, or thermoelectric devices. They could move heat from the sunward surface to the shadow side where it radiates away into space. Done efficiently enough, this could prevent any single surface area from reaching catastrophic temperatures. The engineering challenge is doing this fast enough to handle the pulse heating from a CME impact. You'd need heat transfer systems operating at rates that challenge the limits of what thermodynamics allows. But again, challenging the limits isn't the same as violating them. It's possible, just barely. And if you're an advanced civilization engineering a probe meant to survive close stellar passes, this is exactly the kind of problem you'd solve in the design phase. Let me share something that's not widely publicized but has been circulating in the research community. In late March, during the peak of the monitoring effort, one radio observatory, I'm deliberately not naming which one because the data hasn't been peer-reviewed and the team is still analyzing it, detected a brief radio signal originating from the region of space where 3I Atlas was located. The signal lasted less than 2 seconds. Its frequency was around 1.4 GHz, which is interesting because that's close to the neutral hydrogen line, a naturally occurring frequency that permeates the universe. But this signal had structure, modulation. It wasn't the random noise of natural emission. It was organized, repetitive, carrying what looked like encoded information. The problem is verification. The signal appeared only in one telescope's data. No other observatory was pointing in that direction at that exact moment. Without independent confirmation, it's impossible to rule out local interference, equipment malfunction, or simple statistical noise. The team tried to detect a repeat occurrence over the following weeks. Nothing. One brief whisper, and then silence. So what do you do with data like this? You can't publish it in a major journal without confirmation. You can't claim discovery. But you also can't ignore it. It sits in the analysis pipeline, flagged, noted, studied, waiting for context that might transform it from anomaly to breakthrough. If that signal was real, if it came from 3i Atlas, it changes everything. Because then you're not talking about passive shielding. You're talking about active communication. Maybe not communication aimed at us, maybe internal telemetry, diagnostic transmissions between components of the object's systems, or maybe beacon signals, periodic updates sent back to wherever this object came from, reports on mission status and collected data. The fact that the signal timing correlated very roughly, not precisely enough to claim causation with the third CME impact, is tantalizing. Was it a response? A reaction to the bombardment? An automated damage report? We can't know without more data. But the possibility sits there, this one unconfirmed observation that might be the first direct evidence of artificiality, or might be nothing at all. Here's what's certain. The shield hypothesis, whether magnetic, thermal, or some combination of technologies we can barely conceptualize, is the only framework that coherently explains the full suite of observations. Perfect trajectory maintenance, minimal thermal response, no spectroscopic changes, anomalous cooling curves. Each of these requires sophisticated engineering solutions, and together they paint a picture of an object designed for exactly the kind of mission we've been describing. Deep space probe, stellar investigator, a machine built to survive and study environments that would vaporize anything natural that attempted the same journey. The math works. The physics, while extreme, doesn't violate any fundamental laws. The engineering is far beyond our current capabilities, but that's a statement about us, not about what's possible. So when we ask what kind of shield could protect 3i Atlas through 3 CME impacts, the answer is a shield designed by minds that solved problems we're still struggling to formulate. A shield that operates at the intersection of magnetic confinement, active thermal management, momentum vectoring, and possibly exotic material science. A shield that works so well it makes the object it protects look completely natural to civilizations watching from a distance, unless those civilizations look very carefully at the data and start asking the right questions. Questions that lead inevitably to the places we're going next, the whispers behind the public data, the rumours that won't die, and the possibility that we're not the only ones who noticed something extraordinary happened in March 2025. In the age of social media and instant global communication, keeping secrets about cosmic events is nearly impossible. Not the classified military kind of secrets, those still exist in their fortified silos, but the quieter kind, the things scientists notice and discuss in private channels before they're ready for public consumption. The observations that don't fit, the data that seems too strange to be real, the patterns that suggest something nobody wants to say out loud until they're absolutely certain. Those secrets have a half-life measured in days now. Someone tweets an ambiguous reference. Someone else on Reddit connects it to leaked observation logs. Within hours, you have threads thousands of comments deep, people dissecting telescope time allocations and speculating about what's being hidden. And in the case of 3i Atlas, that speculation reached fever pitch by mid-April. It started with the observation schedules. Amateur astronomers noticed that several major observatories had cleared significant time blocks for unspecified targets in late March. These weren't the normal scheduled observations years in the planning. These were emergency allocations, the kind reserved for transient events like supernovae or gamma-ray bursts. But there were no supernovae visible, no gamma-ray bursts announced, just blocks of telescope time marked with vague descriptors like solar system object or target of opportunity. When you see multiple facilities doing this simultaneously, it tells you something important is being watched. And when those facilities don't immediately publish findings, it tells you something about those observations made them hesitant. Then came the radio telescope logs. Someone with access ethically questionable, legally ambiguous posted what appeared to be scheduling records from an array in the southern hemisphere, showing concentrated observation of a specific celestial coordinate during early April. The coordinates matched 3i Atlas's position. The observation mode was listed as narrowband signal search, which is terminology associated with SETI operations, not asteroid tracking. This created immediate speculation. Was someone looking for communications from the object? Had there been a signal detected that prompted this follow-up? The facility never officially commented, which in the world of academic astronomy is sometimes more revealing than a denial. By late April, multiple Reddit threads and astronomy forums were circulating what claimed to be leaked preliminary reports from various research groups. Most were obviously fabricated bad physics, inconsistent terminology, the kind of thing someone with limited technical knowledge might create to get attention. But a few had details that rang true. References to specific instruments, mentions of data reduction techniques that matched how those instruments actually operate. One purported excerpt described optical polarimetry observations showing the light reflected from 3i Atlas had unusual polarization characteristics, suggesting surface properties inconsistent with typical rocky or icy bodies. Was it real? Impossible to verify without access to the original data, which remained unpublished. Here's where I need to be absolutely clear about something. I am not endorsing these leaked reports as factual. I'm not claiming they represent genuine data, but I am documenting that they exist, that they're circulating, and that their existence is part of the larger story of how information flows and how it gets distorted in modern scientific discourse. The line between legitimate preliminary findings shared cautiously within research communities and sensationalized rumors amplified by social media is increasingly blurred. This creates an environment where distinguishing signal from noise requires more sophistication than most people possess. One persistent rumor that won't die involves planetary defense systems. The story goes that the US Space Force, in coordination with NASA's Planetary Defense Coordination Office, elevated their monitoring status for near-Earth objects in late March following the 3i Atlas events. The claim is that someone decided an object demonstrating anomalous behavior during CME impacts warranted closer attention from a defense perspective, just in case. This would make sense from a precautionary standpoint. If you don't understand what something is or how it's behaving, and it's traveling through your cosmic neighborhood, monitoring it more closely is just prudent risk management. But there's no official statement confirming this. The closest anyone came was a bland press release in early April about routine updates to observation protocols for interstellar objects, which could mean anything or nothing. Social media being what it is, that vague statement spawned theories ranging from the plausible to the absurd. Some suggested military tracking systems were now continuously monitoring 3i Atlas in case it changed course toward Earth. Others claimed secret deep space radar systems had been activated to probe the object's internal structure. A few went full conspiracy, alleging that governments had detected artificial signals and were coordinating a suppression of information to prevent public panic. This last category can be safely dismissed. The global astronomical community is too distributed, too international, too culturally diverse to coordinate any effective information suppression. If there were hard evidence of artificiality, it would leak completely within days. The fact that we're dealing with ambiguous data and competing interpretations rather than smoking gun proof tells you that whatever's happening with 3i Atlas, it exists in that uncomfortable zone where the evidence is suggestive but not conclusive. But there's a different kind of behind-the-curtain story worth telling, one about the scientific process itself. Multiple research groups are currently racing to publish findings about 3i Atlas. Academic publication works on timescales of months. You collect data, analyze it, write a paper, submit it to a journal, wait for peer review, revise based on feedback, and eventually, if you're lucky, your work appears in print. This process ensures quality, but creates a publication gap where significant discoveries can remain in limbo for half a year or more. During that gap, researchers present preliminary findings at conferences. They discuss them with colleagues. They write blog posts and give interviews hinting at what's coming. All of this creates a shadow literature, a layer of scientific discourse that exists in the space between raw data and final publication. For 3i Atlas, this shadow literature is extensive. Conference abstracts submitted for meetings in May and June included dozens of presentations about the object. Topics range from orbital dynamics to compositional analysis to electromagnetic interactions. Some abstracts were tantalizingly vague. Anomalous observations of interstellar object, 3i Atlas, and implications for understanding plasma-object interactions. Others were more specific. Magnetic field estimates for 3i Atlas, based on CME deflection modeling. Reading between the lines of these abstracts, you can piece together the outlines of what various teams think they've found. Most are pursuing natural explanations involving exotic but plausible compositions and properties. A few are more openly speculating about artificial origins, though they couch it in careful language about testing scenarios and null hypothesis rejection. There's also been fascinating activity in the preprint archives online repositories, where scientists post draft papers before peer review. At least 8 papers related to 3I Atlas appeared on the Aircrusca preprint server between late March and mid-May. These papers represent the cutting edge of analysis, the fastest route from discovery to public disclosure. They're not peer-reviewed yet, so they carry caveats, but they're real science done by credible researchers. The conclusions range widely. One paper argues the trajectory stability can be explained by an unusual but natural composition involving high-density metallic core surrounded by insulating regolith. Another presents modelling suggesting the object might be an extinct comet nucleus, with subsurface volatile ices that sublimated asymmetrically to provide thrust cancelling the CME momentum. A third takes the bold step of calculating the power requirements for an artificial magnetic shield and concludes they're challenging but not physically impossible for a sufficiently advanced manufacturing capability. This last paper caused minor uproar in the community, not because of its content but because it crossed the unspoken line. It took the artificial hypothesis seriously, gave it mathematical treatment, and discussed it as a legitimate possibility rather than dismissing it out of hand. Some colleagues praised this as intellectual courage. Others criticised it as giving credence to speculation that would encourage conspiracy theorists. The paper remains in preprint limbo, submitted to a journal but still awaiting review decisions. Its fate will be interesting to watch, because how the peer review process handles speculative but technically rigorous analysis of artificial origins will set precedents for how we discuss these questions going forward. And then there are the things that haven't leaked, haven't been published, haven't even made it to conference abstracts. The quiet conversations between colleagues where they admit uncertainty, where they acknowledge that the data is strange enough to justify considering options they wouldn't normally entertain. I've spoken with researchers who, off the record, confess genuine confusion about what 3I Atlas is. These aren't wild-eyed believers in alien visitation. These are people who've spent careers studying asteroids and comets, who know the full diversity of natural solar system objects, and who are telling you that this one doesn't quite fit. Not dramatically so, not in ways that force conclusions, but subtly, persistently, across multiple lines of evidence, it sits outside the distribution of normal. That's what's really behind the curtain, not a vast conspiracy or hidden proof, just scientists doing their best to make sense of observations that resist easy categorization. The process is messy, slow, and public enough that rumours and leaks are inevitable. Some of those rumours point toward real anomalies. Most are distortions of much more mundane realities. Sorting them out requires patience and critical thinking, both of which are in short supply in the social media age. But buried in all that noise is a signal worth listening for, the signal of genuine scientific uncertainty, confronting something we don't fully understand. And sometimes, though not often, that signal points toward discoveries that reshape what we think is possible. The question is whether 3I Atlas represents one of those moments, or just another cautionary tale about the gap between what we hope to find and what's actually there. Here's the uncomfortable truth that nobody likes admitting in the middle of a mystery. For all the observations, all the telescope time, all the analysis poured into understanding 3I Atlas, we're fundamentally operating with a fraction of the data we'd need to draw definitive conclusions. This isn't negligence, it's not incompetence. It's the reality of observational astronomy when you're dealing with an object millions of kilometers away, moving fast and only visible to us for a limited window of time. We've gathered pieces of the puzzle, some of them fascinating pieces, but the box cover showing the complete picture. That's mostly blank, and understanding what we're missing is just as important as understanding what we have. Start with the most basic question. What is 3I Atlas made of? You'd think after months of observation we'd have a solid answer. We don't. Spectroscopy gives us surface composition, but only for the parts of the surface illuminated by the sun and visible to our instruments. We've got wavelengths showing reflected sunlight, and those wavelengths tell us something about mineral content and surface texture. But interstellar objects are shaped by environments we don't have analogues for in our solar system. They've been exposed to cosmic rays for millions of years. They've experienced thermal cycling in ways that local comets and asteroids haven't. Their surface chemistry might be dominated by processes we've never directly observed. So when we look at 3I Atlas's spectrum and see something that doesn't match any known asteroid or comet class perfectly, is that because it's artificial or because it's natural but foreign to our experience? Without ground truth, without being able to land on the object and directly analyse samples, we're guessing. Then there's the question of internal structure. Everything we've discussed about shielding and momentum conservation depends critically on what's inside that half-kilometre body. Is it solid rock? Is it a rubble pile, a loose collection of smaller fragments held together by minimal gravity? Does it have internal voids, cavities that might house machinery or energy systems? Is the mass distributed uniformly or concentrated in a dense core surrounded by lighter material? These questions matter because they determine how the object should respond to external forces. A rubble pile absorbs impacts differently than a solid monolith. A hollow object has different thermal properties than a solid one. We can estimate total mass from the object's gravitational influence, but that influence is tiny at the distances we're observing from. Our mass estimate has error bars large enough to fit radically different internal configurations. Radar would help. Pointing powerful radio waves at the object and analysing the return signal could tell us about surface roughness, rotation rate, possibly even hint at internal structure if the radar penetrates far enough. But 3i Atlas has been too distant for most of its trajectory for our planetary radar systems to get useful returns. The Arecibo telescope, which could have done this, was destroyed in 2020. The remaining systems, Goldstone in California, the Arecibo successor instruments still being planned, either didn't have the object within range or couldn't allocate the necessary observation time. There was a brief window in April when one facility attempted a radar observation, but the returned signal was weak and noisy. Analysis is ongoing, but preliminary reports suggest nothing conclusive. Maybe the object's surface has unusual reflective properties. Maybe it was just too far. Maybe the geometry was wrong. We don't know. Magnetic field measurements would be revelatory. If 3i Atlas has an intrinsic field strong enough to deflect CME plasma, that field should be detectable by spacecraft with magnetometers passing nearby. The problem is there are no spacecraft anywhere near 3i Atlas. Our solar system fleet the various probes exploring planets, studying the sun, mapping asteroids. None of them had trajectories that brought them within useful range. The closest was a solar observatory that passed within 30 million kilometers in late March. Its magnetometer recorded data, but at that distance, detecting a magnetic field from a half-kilometer object requires the field to be extraordinarily strong, and the signal needs to stand out from the background noise of the solar wind. The data analysis from that flyby is still in progress, classified as high priority by the team managing it, but nothing has been publicly released. Either they found nothing, found something ambiguous, or found something they're still trying to understand. Without access to the raw data, outside researchers can only wait. Here's a critical missing piece that's gotten less attention than it deserves. We don't have continuous observation coverage. Telescopes observe for hours, sometimes days if the object is prioritized, but then they have to move on to other targets. Weather intervenes. Daylight makes observation impossible for ground-based instruments. Orbital mechanics take space-based telescopes out of viewing position. The result is a fragmented timeline. We have snapshots separated by gaps, hours-long gaps, sometimes day-long gaps. If 3i Atlas did something during those gaps, we missed it. Changed its rotation rate, vented gas briefly, emitted signals, adjusted its trajectory minutely. All of these would potentially be detectable if you were watching continuously, but they could easily hide in the observational gaps that define our coverage. This gap problem is especially relevant for the signal detection question. Radio telescopes searching for potential transmissions from the object can only search when they're allocated time and pointed in the right direction. SETI searches traditionally look for persistent signals, or regularly repeating ones because those are easier to detect and confirm. A single brief burst like that unconfirmed 1.4 GHz signal I mentioned earlier could easily be missed entirely if it occurs when no radio telescope happens to be listening, and if the object is smart, if it's designed to minimize detection, it would transmit only briefly and infrequently, specifically to exploit the gaps in our observation coverage. We might be looking at a strategy of intentional evasion, and our fragmented monitoring makes that strategy very effective. There's also embargoed data, a category that exists in the grey space between secrecy and normal scientific practice. Some observations, particularly those made using military or intelligence community assets, don't get publicly released immediately or ever. The US Space Force operates sophisticated tracking systems for monitoring satellites and space debris. Those systems can track objects much smaller than 3i Atlas with impressive precision. If those systems were tasked to monitor this object, and it would be surprising if they weren't, given its anomalous behavior, the data they collected is likely far more detailed than what's available to civilian researchers. but it's also likely classified, at least in terms of what the observations reveal about the capabilities of those tracking systems. There may be researchers with clearances who've seen that data and can't talk about it publicly. Or the data might exist, but hasn't been analysed yet because prioritising a weird asteroid over active satellite tracking and missile warning is a hard sell in a military context. International coordination adds another layer of complexity. Multiple countries operate space observation infrastructure. China, Russia, India, the European Union, Japan all have assets that could contribute to understanding 3i Atlas. Some of this data gets shared through international scientific agreements, some doesn't. Political tensions, competitive advantage concerns, and simple bureaucratic inertia mean that even when data exists, it might not flow efficiently to the researchers best positioned to analyse it. There are almost certainly observations sitting in databases in various countries that haven't been correlated with the broader dataset. Maybe those observations hold the key to understanding what's anomalous about this object. Maybe they're just confirmatory of what we already know. Without access, it's impossible to say. Then you have the most frustrating missing data of all the data we could have collected but didn't, because nobody anticipated needing it. Before 3i Atlas got hit by those CMEs, it was just another interstellar object, interesting but not urgent. Telescope time is precious. Observational priorities are set based on scientific importance and uniqueness. There were almost certainly moments in February and early March when instruments that could have provided valuable baseline data weren't looking at the object because it seemed routine. Now, after the anomalies emerged, that baseline data would be invaluable for comparison. Did the object's brightness change? Did its rotation rate shift? Were there subtle spectroscopic variations that might indicate it was preparing for the CME encounters? We can't answer those questions because we weren't asking them at the time. Hindsight is crystal clear. Foresight is perpetually foggy. Let's talk about what it would take to fill these data gaps. First, you'd need a dedicated mission. Not an observation campaign using existing telescopes, but a spacecraft sent to rendezvous with 3i Atlas. This was actually proposed. Multiple research teams drafted quick response mission concepts in April, as soon as the anomalies became apparent. The problem is speed. 3i Atlas is leaving the inner solar system. Its trajectory is taking it back out into interstellar space. By mid-2026, it'll be too far for detailed observation even with our best instruments. To catch it, you'd need to launch a mission within months, and it would need to be fast, probably using a gravity assist from Jupiter or a solar Oberth maneuver to build up enough velocity to intercept the object before it gets too distant. That kind of mission takes years to plan and costs hundreds of millions of dollars. Convincing space agencies to commit those resources based on intriguing but ambiguous data is a nearly impossible sell, especially when the scientific return, while potentially enormous, is also highly uncertain. There was serious discussion about this in late April. NASA's Planetary Science Division held internal meetings. ESA's Science Directorate did the same. China's space program apparently conducted feasibility studies. But by early May, the consensus had formed that it wasn't going to happen. Too expensive, too risky, too fast a decision timeline for bureaucracies that normally operate on 5-year planning cycles. There were proposals for compromise missions, maybe not a rendezvous, but a fast flyby that could at least get close enough for high-resolution imaging and magnetic field measurements. Even those didn't gain traction. The moment passed. 3i Atlas will leave our observational range carrying its secrets with it, and we'll be left with the data we managed to collect during its brief passage through our neighbourhood. This is the reality of astronomy and the study of transient phenomena. We don't get second chances. We don't get to rewind time and position our instruments better. We work with what we captured in the moment, and we accept that our conclusions will always be provisional, always subject to the limitations of incomplete data. For 3i Atlas, those limitations are significant enough that definitive answers may remain permanently out of reach. We can build models, we can explore hypotheses, we can make educated guesses, but truly knowing what this object is and what those CME encounters meant, that might be something we have to live without, unless, of course, the object comes back, or others like it arrive and we're better prepared next time. Because one thing the gaps in our data absolutely can't tell us is whether 3i Atlas is unique, or just the first of many that we've been able to observe carefully enough to notice the anomalies. And that uncertainty leads directly into the question everyone's been dancing around since March. What exactly could this thing be? Let's put all the speculation aside for a moment and approach this systematically. We have an object. It behaves strangely under specific circumstances. It raises questions that our standard models don't easily answer. So what are the actual possibilities? What could 3i Atlas be that would explain not some, but all of the observations? This is the section where we lay out the competing hypotheses, examine their strengths and weaknesses, and try to be honest about which ones fit the data best. I'll start with the natural explanations, because they're always the right place to start, and then we'll work our way into more speculative territory. Fair? Hypothesis 1. 3. I-Atlas is an ultra-dense fragment of stellar material. Maybe it's a piece of a white dwarf blown off in some ancient cataclysm and wandering the galaxy ever since. White dwarf material is incredibly dense, hundreds of thousands of times denser than normal rock. A half-kilometre chunk would have enormous mass despite its small size, and that mass means high inertia, which means resistance to changes in motion. Could this explain the lack of deflection during the CME impacts? Possibly. The more massive something is, the harder it is to push around. But here's the problem. If 3i Atlas had white dwarf level density, its gravitational influence would be detectable. It would perturb the orbits of anything that passed near it. We've seen no such perturbations. Its gravitational signature is consistent with ordinary rocky or metallic density. So unless there's some exotic physics allowing it to have high inertia, without high mass and no known physics does this. The ultra-dense fragment hypothesis doesn't work. Hypothesis 2. It's a fragment with an unusual magnetic field. Some natural objects, particularly certain types of meteorites called pallasites, contain nickel-iron compositions that can retain strong permanent magnetization. If 3i Atlas is essentially a giant magnet, perhaps that field is strong enough to interact with the charged particles in CME plasma, creating deflection forces. This would explain the apparent plasma shielding. The problem is quantitative. The magnetic fields in magnetized meteorites are measured in microtesla to millitesla ranges. To deflect CME plasma effectively, you need fields thousands of times stronger. There's no natural magnetization process that produces those field strengths in objects this size. You'd need something like a fragment of a neutron star's crust. But again, that brings us back to the density problem. The hypothesis is physically conceivable, but requires such extreme conditions that it becomes statistically implausible. Hypothesis 3. 3. I-Atlas is a primordial object with exotic composition. The early universe, in the moments after the Big Bang, produced conditions that don't exist anywhere now. Incredibly high densities, temperatures, and pressures that could potentially create forms of matter that are stable but exotic. Quark nuggets, dark matter clumps, hypothetical particles that we've theorized but never detected. If 3i Atlas is made of something like this, its behavior might not follow the rules of ordinary matter. This hypothesis has the advantage of being virtually unfalsifiable. You can always claim, maybe it's made of stuff we don't understand. But it has the disadvantage of requiring the existence of exotic matter that we've never confirmed, and then requiring that this exotic matter somehow formed into a half-kilometre object and ended up on a trajectory that brings it through our solar system. The compounding improbabilities make this a last resort explanation, something you invoke only after exhausting all conventional possibilities. Hypothesis 4. It's an extinct comet with unusual internal structure. Comets are icy bodies, but not uniformly so. They have rock and metal mixed with the ice, and as they age, losing volatile material with each solar pass, they can develop hard outer crusts of refractory material that insulates the interior. If 3i Atlas is an ancient comet that's already lost most of its ice to sublimation over millions of years of wandering, it might look rocky on the outside but still have pockets of subsurface volatiles. When the CMEs hit and heated the surface, maybe those subsurface ices sublimated asymmetrically, creating jets that provided exactly the right counterthrust to cancel the incoming momentum. This is actually one of the more clever natural explanations, because it uses the object's response to the CMEs as part of the shielding mechanism. The object isn't passively resisting, it's actively venting gas in response to heating, and by chance those jets produce forces that balance the impact momentum. The challenge with this hypothesis is timing and symmetry. For the jets to exactly cancel the CME momentum, they'd need to start at precisely the right moment, with precisely the right thrust direction, and sustain for precisely the right duration. Once might be luck. 3 times, across 3 separate CME events with different impact angles and durations. That strains credibility. Plus, we should see spectroscopic evidence of the outgassing emission lines from water vapour, carbon dioxide, cyanide compounds, whatever volatiles were sublimating. No such evidence appeared in any of the observations. So while this hypothesis is physically possible, it requires a series of coincidences that make it unlikely unless there's some mechanism we're missing that makes the response more deterministic than random. Hypothesis 5. It's a metallic asteroid with specific electromagnetic properties. Certain metal compositions, particularly those involving conductive metals in the right structural configurations, can exhibit interesting electromagnetic behaviours. When exposed to changing magnetic fields, they generate eddy currents that produce their own magnetic fields opposing the change. This is the principle behind electromagnetic braking systems. If 3I Atlas has the right metallurgical structure, the changing magnetic fields in the CME plasma might induce eddy currents that generate an opposing field strong enough to provide some shielding. Combined with the object's thermal mass distributing the heat efficiently, this could potentially explain both the trajectory stability and the moderate thermal response. This hypothesis is appealing because it relies only on well-understood physics and material properties that, while unusual, aren't impossible. The downside is it still requires a fairly specific combination of composition, structure, and geometry to work as effectively as observed. It's possible, but it narrows the range of what 3I Atlas could be to a very particular type of object. Now we arrive at the hypothesis that some researchers won't say in public but discuss privately. Hypothesis 6. It's artificial. A probe, a craft, a manufactured object sent from somewhere else for purposes we can only guess at. This hypothesis explains everything. The trajectory stability is active correction using propulsion systems. The magnetic shielding is generated technology. The thermal management is engineered heat distribution. The possible radio signal is telemetry. Every anomaly that requires tortured explanations under natural hypotheses becomes straightforward under the artificial one, and that's precisely why it's so controversial, because invoking intelligence is seen as giving up, as abandoning the search for natural explanations prematurely. The history of astronomy is full of phenomena that seemed inexplicable until we understood them better. Pulsars were briefly considered possible alien beacons until we realized they were rotating neutron stars. Fast radio bursts mystified us until we found natural astrophysical sources. Claiming aliens did it has been wrong every single time in the past. Why should this time be different? Here's why. Because for all those past mysteries, once we understood the natural explanation, it made sense. Pulsars fit into our models of stellar evolution. Fast radio bursts fit into our understanding of magnetars and neutron star mergers. The explanations once found were satisfying. They explained not just the phenomenon in question, but made predictions about related phenomena that we then confirmed. With 3I Atlas, the natural explanations being proposed don't have that quality. They're forced. They require special circumstances, unlikely coincidences, or properties at the edge of physical plausibility. That doesn't prove the artificial hypothesis is correct, but it means we can't dismiss it simply by appealing to historical precedent. Sometimes the extraordinary explanation is correct because the ordinary ones genuinely don't fit. What would artificial mean in practice? It means somewhere out there, perhaps hundreds or thousands of light years away, perhaps even in a different galaxy, if we're talking about a probe millions of years old, there was a civilization with technology advanced enough to build something that could cross interstellar space, survive for timescales that dwarf human history, and operate autonomously in environments that would destroy anything we could currently build. It means that civilization either still exists, in which case the galaxy harbours intelligence besides us, or existed and is now gone, in which case we're looking at an ancient artifact, a message in a bottle from a voice that's gone silent. Either possibility is profound, either one changes the context of human existence in the universe. And here's the thing that keeps me personally awake some nights thinking about this. If 3I Atlas is artificial, it means we're being studied. Those CME impacts weren't accidents from its perspective. They were data collection opportunities. It measured our sun's behaviour. It tested the local space environment. Maybe it's been broadcasting what it learned, narrow beam transmissions aimed back toward wherever it came from, messages that will take centuries or millennia to arrive, but will eventually tell some distant civilization about this star system, its planetary arrangement, its level of technological development based on electromagnetic signatures in our planetary magnetospheres. We're not just observers in this scenario, we're being observed. Our solar system is a data point in someone else's survey, and that idea, that shift from cosmic isolation to cosmic surveillance, is perhaps more unsettling than the confirmation of intelligence itself. But let's be clear, we don't have proof. Everything I've described is circumstantial. Anomalies are not evidence of artificiality. Strange behavior is not confirmation of intelligence. We need more data, better observations, ideally a close-up mission that could settle this definitively. Until then, the artificial hypothesis remains exactly that, a hypothesis, one possibility among several, arguably the one that best fits the full data set but not proven beyond reasonable doubt. Science requires skepticism, demands high standards of evidence, and rightly rejects claims that outrun their data. So I present this not as conclusion but as option, as a framework for thinking about what we're seeing that deserves consideration alongside the natural explanations. Because whether 3i Atlas is a weird rock or a machine from the stars, the important truth remains the same. It's shown us that our solar system can be visited by objects that challenge our understanding. It's demonstrated that nature or intelligence produces phenomena at the edges of what we think possible. It's reminded us that the universe is far stranger, far more complex, far more full of surprises than our neat theoretical models usually admit. And as it speeds away from us, back into the darkness between stars, it leaves behind not answers but better questions. And sometimes that's the more valuable gift. Which brings us to the final piece of this story, what it all means, not just for science, but for how we think about our place in the cosmos, and what we do next with the knowledge that out there, in the vast dark, things are happening we don't understand, and may never fully understand, but can at least witness in moments like this. There's a moment that happens in every profound mystery, where you step back from the details and ask the bigger question. Not what happened, but what does it mean? For months now, we've been tracing the data trails of 3i Atlas, the trajectory, the impacts, the anomalies, the competing explanations. But zoom out far enough and you see something that transcends this single object. You see a pattern of interaction between matter and energy, between object and environment, between visitor and host that speaks to something fundamental about how the universe operates. The sun threw 3 punches at a passing stranger. The stranger didn't flinch, and then the sun changed. What does that tell us about the nature of existence at cosmic scales? Let me offer you a perspective that's admittedly philosophical but grounded in physics. The universe is not made of isolated objects moving through empty space. It's made of fields, electromagnetic fields, gravitational fields, quantum fields permeating every cubic centimetre of existence. Objects are just localized disturbances in those fields, concentrations of energy that we perceive as matter. When 2 objects interact, what's really happening is their fields are overlapping, exchanging energy and momentum through mechanisms we've spent centuries learning to describe mathematically. Most of the time, these interactions are simple, predictable, covered by equations we teach in undergraduate physics. But sometimes, rarely, tantalizingly, you encounter interactions that push the boundaries of those equations, that hint at complexity we haven't fully mapped. The 3i Atlas events might be exactly this. Not a simple case of rock meets plasma following straightforward collision dynamics, but a complex field interaction where electromagnetic properties, magnetic configurations, and possibly information exchange occurred at levels we couldn't fully observe. The sun's coronal mass ejections aren't just particles moving through space. They're magnetized plasma, carrying frozen-in magnetic field lines that connect back to the sun's interior. When that plasma encounters an object with its own magnetic field, those field lines can reconnect, merge, create new topologies that allow energy to flow in unexpected ways. Maybe what we witnessed wasn't an object being hit and passively absorbing the impact. Maybe it was an active electromagnetic dialogue, a conversation in the language of magnetic fields and plasma instabilities, where both participants, the sun and the object, exchanged information, encoded in ways we're only beginning to understand. This reframing changes the question. Instead of asking, how did 3i Atlas survive? We ask, what did the sun and 3i Atlas communicate during those encounters? If the object was probing the sun's magnetic field structure, the CME impacts were its interrogation signals, deliberate perturbations designed to map how the star responds to stress. The sun's subsequent magnetic reconfigurations weren't reactions in an emotional sense, but physical responses to the perturbations, feedback that the object could measure and analyze. And if the object transmitted data afterward, the unconfirmed radio signal, or others we missed, it was reporting its findings, sending a message that encodes information about stellar behavior in this particular system. Now extrapolate that idea. If 3i Atlas is indeed artificial, it's likely not alone. If one civilization developed the capability to send interstellar probes, and if those probes can operate for millions of years, then statistically there should be many such objects wandering the galaxy. Most we'd never notice because they don't pass through our solar system, or they do but we're not looking at the right time, or they're designed to be stealthier than 3i Atlas happened to be during its CME encounters. We've only recently developed the technology to detect interstellar objects at all. Oumuamua in 2017 was the first confirmed one. 2i/Borisov in 2019 was the second. 3i Atlas is the third. 3 detections in 8 years suggest they're not rare. They're common, and we're just now getting good enough at observation to spot them. If even a small fraction of interstellar objects are artificial probes, it means the galaxy is crisscrossed with surveillance networks, ancient or ongoing projects, by civilizations mapping the cosmos star by star. Some of those civilizations might still exist, monitoring the data streams from probes launched millions of years ago. Others might be extinct. Their probes the only remaining evidence they ever existed. Robotic archaeologists documenting a universe that outlived their creators. This is the Bracewell probe hypothesis, proposed decades ago by radio astronomer Ronald Bracewell as an alternative to traditional SETI radio searches. Instead of broadcasting signals hoping someone hears, you send physical probes that can travel to star systems, observe locally, and report back or wait for technological civilizations to emerge and make contact. The implications are staggering. If we're living in a galaxy where such probes are common, then every time we advance technologically, every time we achieve a new milestone, first radio, first spaceflight, first nuclear capability, first artificial intelligence, we're potentially triggering new levels of interest from whatever monitoring systems happen to be nearby. Maybe 3i Atlas came through now, during this particular decade, not by chance, but because something we did in recent years flagged our system as worth investigating. Maybe the proliferation of satellites in Earth orbit created an electromagnetic signature that changed how we appear to distant observers. Maybe our increasingly powerful radar and radio emissions painted a picture of emerging technology that warranted a closer look. Or maybe it's pure coincidence, and we're pattern matching where no pattern exists, seeing intention in randomness because our brains are wired to find agency everywhere. But let's sit with that uncertainty rather than rushing to resolution. The fact that we can't definitively distinguish between these possibilities is itself profoundly important. It means we're at a moment in human history where contact with non-human intelligence has transitioned from science fiction to scientific hypothesis. We're not there yet. We don't have proof. But we have enough ambiguity, enough suggestive evidence, enough anomalies that responsible scientists can discuss artificial origins in technical papers without being dismissed. That's new. That's a threshold we've crossed in the past few years, and 3i Atlas might be the case that pushes us further across it. So what do we do with this? How do we proceed knowing that objects like this are out there, passing through our cosmic neighborhood, behaving in ways we don't fully understand? First, we improve our detection capabilities. More telescopes, better sensitivity, faster response times when something unusual is spotted. We need systems that can detect interstellar objects earlier in their approach, giving us months or years instead of weeks to study them. We need dedicated funding for rapid response missions that can launch on short notice to intercept interesting targets before they slip away into the dark. These are engineering and funding challenges, not physics challenges. We know how to build the instruments. We know how to fly the missions. We just need to decide it's worth the investment. Second, we change our priors. For decades, the assumption in astronomy has been that everything we observe has natural explanations, and we should exhaust those explanations before considering artificial ones. That's been a good rule. It's kept us from seeing aliens in every weird pulsar signal. But it might be too conservative now. We might need a framework that says, if we observe X, Y, and Z characteristics together, that's sufficient evidence to seriously investigate the artificial hypothesis, even if natural explanations haven't been completely ruled out. This doesn't mean lowering standards of evidence. It means recognizing that artificial objects, if they exist, will have characteristic signatures, and those signatures should be on our checklist alongside stellar physics and planetary science. Third, we prepare for the conversation. If probes like 3i Atlas are mapping the galaxy, and if some of them are still reporting to active civilizations, then at some point, maybe decades from now, maybe centuries, maybe tomorrow, we might receive a response. Not in the form of little green men landing on the White House lawn, but in the form of a signal, a pattern, a probe altering its trajectory toward Earth, because it detected our curiosity. We need protocols for how to handle that, not government secrecy and panic, but transparent, international, scientifically grounded processes for verification, interpretation, and response. This isn't fantasy. The SETI community has developed post-detection protocols for exactly this scenario. We should update and expand them for the reality of physical probes rather than just radio signals. And finally, we sit with the wonder, because regardless of whether 3i Atlas is a rock or a robot, whether it's natural or designed, the fundamental truth remains awe-inspiring. The universe is big enough and old enough to contain things that astonish us. The laws of physics permit structures and behaviors we haven't imagined yet. The gap between what we know and what exists is vast, humbling, and exhilarating. 3 billion-ton plasma waves hit an object half a kilometre across, and it didn't move. The sun noticed. We noticed. And now we're changed by the noticing, by the realization that our textbooks aren't complete, our models aren't final, and the cosmos still has capacity to surprise us. This is why we do science. Not for the comfort of confirmed theories, but for these moments at the edge, where data and mystery intersect and create questions that pull us forward. 3i Atlas is leaving us now, accelerating back into interstellar space, carrying whatever knowledge it gained during its months observing our sun. We won't see it again. In a few years, it'll be too far for even our most powerful telescopes to track. It'll become a catalogue entry, a footnote in astronomical records, a case study in graduate seminars about anomalous objects and the limits of observation. But the questions it raised, those persist. They'll drive observation campaigns for the next interstellar visitor. They'll motivate mission proposals to NASA and ESA. They'll fill papers and conferences and late-night discussions between researchers trying to make sense of the universe. And somewhere out there, moving through the dark at speeds we can barely achieve with our most ambitious spacecraft, 3i Atlas continues its journey, silent, autonomous, carrying inside its half-kilometre frame either the random results of natural processes or the intentional design of minds we've never met. Either way, it's a miracle. Either way, it expands the boundaries of what we know is possible. Either way, it reminds us that we're part of something bigger than ourselves, participants in a cosmic story that started billions of years before we existed and will continue long after we're gone. The sun threw 3 punches at a passing stranger. The stranger taught us that reality is stranger than we imagined. And that lesson, that gift of expanded possibility, that's what we carry forward. So I'll end with this. Stay curious, stay skeptical, question everything, but remain open to answers that surprise you. The universe is not obligated to make sense on timescales convenient to human lives. Some mysteries take generations to solve, some may never be solved. But the pursuit of understanding, the willingness to stand at the edge of knowledge and peer into the unknown, that's what makes us human. That's what transforms us from biological accidents into conscious witnesses to cosmic wonder. 3i Atlas was a visitor. Brief, enigmatic, gone. But visitors leave traces. They change those they visit. We're changed now. We know the solar system can host mysteries that challenge our deepest assumptions, and that knowledge doesn't close doors. It opens them. To discovery, to possibility, to the humbling joy of realizing we live in a universe far more interesting than we dared believe. Tell me in the comments, where are you watching from? What's your theory about what 3i Atlas really was? Are you ready for the next one, the next interstellar visitor that might arrive tomorrow or next year? With new puzzles, new data, new opportunities to understand, hit that subscribe button because this story isn't over. It's just beginning. And when the next object appears, when the next anomaly emerges from the data, we'll be here, analysing it together, pushing at the edges of what's known, reaching toward what's possible. The universe reacted. We're reacting back. And in that exchange, that dialogue between cosmic forces and human curiosity, something profound is happening. Something that might just be the most important thing our species has ever witnessed. Thank you for staying with me through this journey. Thank you for caring about evidence and questions and the beautiful uncertainty of real discovery. Now go look up at the night sky and wonder what else is out there, passing through the dark, waiting for us to notice.